Welcome to EDU World Space.
This question gives us the molecule dmpe, which stands for dimethylphosphinoethane, and in part A asks us to draw the Lewis structure for dmpe and compare it to ethylene diamine as a coordinating ligand. So we'll start out with the Lewis structure of this guy. We typically go from right to left. I'm going to go ahead and start with this P right here. So we'll have the P that has two CH3s, excuse me. So we'll have CH3, CH3, and then a CH2. I'm going to go ahead and erase that. And these H2s are going to come out. H. We have another CH2. And this P is going to have a lone pair on it, so we'll draw that. We're going to have one more, and then it's essentially a mirror image from this half over. So we have P, draw the lone pair, the CH3, and then a CH3. It asks us to compare this to ethylene diamine, or EN, which is N, the lone pair, it's an NH2, CH2, CH2, and NH2. So they're both bidentate ligands. This ethylene diamine is less bulky. It doesn't have as much on it. For example, these H2s off of the N take up much less space than these CH3s that are off of our P. However, this dmpe is a stronger electron pair donor because this phosphorus is less electronegative than this nitrogen. We're then asked in part B to determine the oxidation state of a compound, and we'll go ahead and go over to a second page for that. So part B gives us this compound, Na2, MOCN2, CO2, dmpe, and asks us to determine the oxidation state of the MO, where the Na has a +2 charge, the Cn has a -2 charge, the CO does not contribute a charge, and the dmpe does not contribute a charge, and therefore our MO has an oxidation state of 0. It's neither positive or negative. We're then asked to sketch the structure of this molecule and with all of its isomers. And so to do that, I'm going to move this up over here. I'm going to draw across the bottom here, where we're going to start with our metal ligand. We have MO. We know that it's an octahedral because there's 6 things coming out of it, 2, 4, and then this is a bidentate ligand, so 6. We have 1, 2, 3, 4, 5, 6. I'm just going to start off by doing just whatever feels good. So we have this CN, make it across from the CN. So this would be a trans configuration. So we have the CO, COs are next to each other, and then this dmpe I'm going to draw as a P, and a P with a line going between the two. Another isomer you could imagine is where the CNs are next to each other and the COs are across from each other, are trans. So we're going to have this MO back and coming in front, where we leave the P's, the dmpe the same. We have the CO, CO, CN, CN. We could also imagine the relationship between these CNs being different in regard to where the dmpe is. So for that, MO where we're still going to have the P here, and then we're going to put one CN here, and then one CN here, one CO here, and one CO here. And that's only different in the location relative to this dmpe. Now, this molecule, if you do a mirror image of it, we'll get another isomer. So to do that, we'll have MO down, 2 going out of the page, 2 going into the page, 2 going out of the page, where again, we'll just do the mirror image of this guy. We have CN, CN, CO, CO, and then our P connected to be the dmpe. And if you look at these two, they are not superimposable, and so they are isomers of each other.